My name is Noureldin Hassan. I'm a PhD student at the University of Central Florida. And today I'm presenting our paper, WarmCache, Exploiting STT-RAM Cache for Low-Power Intermittent Systems. Energy harvesting systems has emerged as an alternative to battery-equipped IoT. And these batteryless devices collect energy from the environment to charge a capacitor as its energy storage. These energy sources could include RF signals, solar energy, thermal energy, kinetic energy, among others. But one critical challenge facing energy harvesting systems is that they are prone to frequent power failure due to the instability of the power sources. If we have a program, while the program is running, the system will face a power failure, which will make it lose all the volatile data, forcing the program to start over from the beginning until we reach another power failure that leads to the same scenario, causing a kind of denial of service. A state-of-art solution for this problem is just-in-time checkpointing. The idea is to checkpoint volatile data to a non-volatile memory before power failure and to resume the program from where it was interrupted when the power returns. As we can see, the system consists of a capacitor, a voltage monitor to measure the voltage of the capacitor, a non-volatile memory, registers along with non-volatile flip-flops, and a controller. When the system is running, the register will be filled with data. Once the capacitor voltage reaches the checkpointing threshold shown as voltage backup in the graph, the voltage monitor sends this and sends a signal to the controller in order to checkpoint the volatile data to the non-volatile flip-flop. And once we reach voltage off, the system is turned off. Then, when the capacitor is fully recharged, the data is returned back to the register, and then the system is powered on again and continue execution. Now, using a non-volatile data can cause high latency and energy cost. So one idea to improve performance is to include a volatile cache like SRAM, thus reducing the non-volatile memory access. But the problem is volatile caches can face crash consistency issues in energy harvesting systems. When the system is running, data will be fetched to the SRAM cache. Once the system is turned off, the SRAM cache would lose all data, which can cause crash consistencies when the power returns, in case some data have not been persisted yet. So the state-of-art solution includes an SRAM cache along with a crash consistency support. One such solution is replay cache, which uses a compiler-directed approach by dividing the program to a series of regions with no overwritten stores. And then when the power returns, it replaces the stores using the checkpointing registers. Another solution is write-like cache, which uses a specialized write policy by limiting the number of dirty cache lines and flushes these lines to the NVM before the power is interrupted. It also adaptively changed this limit based on the quality of the power sources. But even with the crash consistency support, there is still a problem that all volatile cache solutions suffers, called the cold cache phenomenon. As we said, when the program is running, the SRAM would be filled with data. Then when it is turned on, the SRAM would lose all data. Then when we return the power again, we are not going to face crash inconsistencies because we have the available support. Instead, we're going to face comparsely misses in order to refill the cache that is empty or cold. And we can see here in the graph for the cache miss rate that both replay cache and write-like cache face a cold cache penalty in a form of comparsely misses of a rate of around 17% and 15% respectively. For this purpose, we introduce WarmCache, a cache designed to address the cold cache phenomenon. The idea is to use an STT-RAM cache with the relaxed non-volatility, meaning it has a shorter retention time. And this retention time is tuned to be long enough to cover the power-off period, thus avoiding the cold cache penalty. We also introduce a compiler-directed approach for STT-RAM retention failure correction and use the compiler techniques of region stitching and region splitting to form idiosyncratic regions optimized for performance. STT-RAM is an emerging non-volatile memory technology. One of its main advantages is that it has very low leakage power consumption, but it does suffer from a high write energy. This can be mitigated by relaxing its non-volatility through tuning a parameter called thermal stability. Thermal stability is basically a measure of the degree of thermal fluctuations in the memory. And since retention failures in STT-RAM is mainly caused by the thermal fluctuations, the lower the thermal stability, the shorter the retention time. The advantage of doing this is that by decreasing the retention time, the write energy decreases, thus improving performance compared to a non-volatile STT-RAM. On the other hand, the short retention time can get short enough that it will increase the probability of retention failure. So it is necessary to periodically scrub the memory using an error correcting code to correct for these retention failures. Which means that tuning the retention time in the relaxed STT-RAM involves a trade-off between write energy and the scrubbing cost. We can get a relation between the thermal stability and the total execution time, summarizing these costs, shown here in the equation in the graph. At high thermal stability, the STT-RAM would be non-volatile, and then with decreasing thermal stability, we get a decreasing execution time due to decreasing write energy until we reach an optimum point after which any decrease in the thermal stability increases the execution time due to high scrubbing cost. A question we can have, is this short retention time short enough to cause multi-bit errors or not? The answer is yes. This short retention time can cause multi-bit errors, which can lead to corrupted cache lines be persisted to the non-volatile memory. One possible solution is to use a multi-bit ACC rather than a single-bit ACC. Another solution is to use a write-through policy in order to persist a clean copy right away to the non-volatile memory and later check for errors using a detect-only cyclic redundancy check. But the problem is that both solutions are costly, leading to a significant overhead. So instead, we introduce a compiler-directed approach with a lightweight hardware support that relaxes both the correction and the persistence to the region level. In order to ensure region-level error correction, the WarmCache compilers partition the program into a series of idempotent regions, and in this way, in case a multi-bit error occurs, we can correct them by re-executing the region. We have two possible scenarios for errors. We could have single-bit errors. We check and correct dirty cache lines before the region end using an efficient single-bit error ACC. The other scenario, we could have multi-bit errors. We use a cyclic redundancy check, CRC31, in order to check the dirty cache lines before the region end. And in case we detect an error, we re-execute the region from the beginning in order to recompute the correct values. Otherwise, we continue execution. And because these multi-bit errors are still rare, these re-executions are going to be rare, limiting the scrubbing overhead. Now, one question we could have about this kind of partitioning, is it safe to overwrite stores across these regions? WarmCache ensures this by region-level persistence, meaning that all stores in the region are persisted at the region end before starting at any new region. This can cause an increased latency between the regions. So in order to reduce this latency, we asynchronously write back the stores to the memory. If we see this example, the program starts. Once a store is reached and stored in the cache, we start the write back right away using the write back function call and overlap it with other instructions so that when we reach the region end, we persist the data to the non-volatile memory. Then we can start a new region and we reach another store, and again, we start the write back right away and overlap it with other instructions. And in case we reach the region end and the data is not persisted yet, the program stalls until the write back is finished and the data is persisted. And then we can start a new region. Another issue with this kind of partitioning is idempotent regions are very short. As we can see in this example, we have to put a boundary to cut each write after read dependency in order to ensure the idempotence. But that means that we have to scrub and checkpoint at each of these region boundaries, causing a high scrubbing and checkpointing cost. In order to solve this, we use a compiler technique called region stitching. The WarmCache compiler stitches small regions to form larger regions and uses an undo lock to deal with write after read dependencies in order to preserve the idempotence. As we can see in this example, we have two regions with R2 having a write after read dependency across these regions. So in order to stitch them, We log the value of R2 from the first region to the undo log. Then we stitch the two regions together. In case we want to re-execute the region in order to correct for errors, we return back the value of R2 to its starting value using the logged value in the undo log, and then we remove this value from the undo log. In this way, we can re-execute the stitched region while preserving the item potence. But still, these large regions formed by region stitching can have a scrubbing overhead large enough that it can exhaust the system available energy before being finished. One scenario this can happen is that we can have a large region with an execution time longer than the scrub interval necessary to ensure reliability. That means an increased retention probability failure at the region boundary, leading to repeated re-executions. Another scenario is that we could have many stores in the region, which can lead to too many dirty cache lines to be scrubbed at the region boundary. We solve this using another compiler technique called region splitting. The WarmCache compiler measures the execution time from the beginning of the region, and once it reaches the scrub interval, it splits the region in order to ensure the total execution time is less than the scrub interval. It also counts the number of stores, and once it reaches a prefix maximum, we split the region in order to ensure the number of stores is less than this maximum, this prefix maximum. Now we move to the evaluation. We tested WarmCache using the MVP simulator for non-volatile processors built on Gen 5 with ARM architecture. We used MVSim to get the cache and memory parameters, and we have here the parameters for different STT-RAM caches. We included in our simulation a 4 kilobyte instruction data caches with 64 byte cache line and a 64 kilobyte PC-RAM main memory. We tuned our retention time to be 1 hour average retention time. And we used application from MyBench and MediaBench benchmark to test WarmCache. And this was done on RF and thermal power traces. To test for performance, we compared with write-light cache and replay cache, both state-of-art solution for volatile caches. And to test for reliability, we compared with Sudoku, which is a state-of-art solution for STT-RAM retention failures. And as we can see, WarmCache outperforms all the volatile cache solution by having a higher normalized speedup compared to a non-volatile cache, with a 1.3 speedup compared to the best state-of-art solution. And we can see here the reason for this is that WarmCache avoid the cold cache penalty that all the volatile cache solutions suffer, but avoid the cache miss rate due to the comparsely cache misses. And to test for reliability, we measured the failure probability while varying the thermal stability and compared it with different ACC support, and we can see that WarmCache have a reliability comparable to the best state-of-art solution. In conclusion, we introduced WarmCache, a cache designed for energy harvesting system to address the comparsely cache misses by leveraging a relaxed STT-RAM cache. And our experiments demonstrate that WarmCache reduces comparsely misses and improves performance by 1.3, 1.4 speed up on average compared to the state-of-art cache designs. Thank you.